Recording has begun.
Mr. Recording.
Alright, over the past couple of days, we have been focusing on our discussion of nuclear energy. And we said that nuclear energy is the energy associated with the nucleus of an atom. Why does the nucleus of an atom contain a lot of potential energy? Chris, go ahead.
You have all the protons repelling each other.
Right. All the protons are there. They're all trying to repel each other. Right. Under most circumstances, the strong nuclear force holds them together. But when we get too many protons, it just can't anymore. And so those protons start repelling each other. Those protons move apart. And as they move apart, we can do something with them. That's energy. Sam, go ahead.
Is like potential energy gravitational or elastic, or is it just neither?
It's kind of more like elastic, I guess, in a way that, with something that's elastic, if you stretch it out, if you hold it stretched, it'll stay that way. But if something happens and you can't hold it anymore, then it'll snap back that way. Although it's kind of the same idea with gravitational, depending on how high you hold it, right? Same idea that it's like waiting, and then if we release it, something might happen. But, obviously a little bit different in both. It's not fine. All right. Over the past couple of days, we have spent a good amount of time talking about this idea of nuclear fission. And to summarize nuclear fission, talk about the idea that we're taking this big nucleus, a radioactive nucleus. Not any radioactive nucleus, only certain radioactive nuclei, uranium-235, plutonium-239. And if we run a neutron into them, that big radioactive nucleus will split into two smaller nuclei, and then two neutrons that come out of it. Okay? Go ahead, Elsa.
Where does that neutron come from?
We said that there are certain things out there that when they decay, they give off neutrons. They're unstable the way they are, and they give off neutrons as well. So if we have some of that material, we can put it, for lack of a more scientific description, we basically put it in a box, and it's giving off neutrons inside the box, and then if we poke a hole in the box, neutrons will come out of the box. Okay? I mean, that's obviously I'm oversimplifying it, but that's the gist of it. Parker, go ahead.
Where exactly would you find, uranium?
Okay. They exist. Well, uranium exists out there in nature. Plutonium we have to make in the laboratory. But the problem is with uranium-235, and I think we discussed this too, that uranium is like a rock. It's just it's in the ground and blah blah blah. We mine it just like we mine copper or silver or gold. But most of the uranium that's in the ground is uranium-238, which doesn't do this fission reaction. If we run a neutron into uranium-238, right, basically what happens is the neutron sort of globs into the nucleus, right? Don't worry about Mr. Shoulders doing the neutron basically globs into the nucleus, and then like a little piece sort of globs off. It doesn't split into two pieces like that. So, Parker, the point being that we have to go through a process in order to enrich the uranium to make it more uranium-235. But only certain one of these are. You're going to see her again in a couple minutes. But that idea being that not any nucleus will do it, only certain nuclei will do it. Okay? But as it does it, it releases a bunch of energy because of this whole idea of mass energy equivalence that we discussed. That if we can get energy and convert it into mass, we generally get a lot of mass out of a lot of energy out of a very small amount of mass. Okay? And that, if we look, I thought they were the
broken
best.
one.
I thought they were the best.
In the background, yeah.
But the point being that if we take a look at the mass of these reactants, this neutron and this nucleus, and the mass of these products, it's not the same, right? The mass goes down a little bit, that mass is converted into energy, that's where it comes from. The big point being the whole idea of the chain reaction, that if we can use these two neutrons to then run into other uranium-235s, now we get more neutrons, and we run them into more uranium-235s, and then we get more neutrons, run them into more, each time releasing more and more energy. Okay? And that's how we got into the power plant idea, right? Okay? Did we finish up all of the outline part of the power plant? No.
Oh, what?
Yeah.
All right, so C, nuclear reactor uses to control chain reaction. D, the energy released by the nuclear fission is used to turn water into steam or to heat water. Okay? And then that steam that is produced is used to do what? Turn a generator. Just like the steam that is produced in a coal power plant, the only difference being, right, how do we heat the water? That's the difference. Good there? Dominic, go ahead.
I have a question.
Question.
Do you know how it's the turbine that the steam pushes that makes the generator go?
Yep.
Is it possible that we can have like people pushing the turbine?
Sure. Absolutely.
Why don't we do that? Because that's energy efficient.
Well, that's true, but you have to feed all those people and make sure they don't get tired and all that kind of stuff, you know?
Yeah, but like if we're going to a huge crisis, we could do that.
That's true. Although, the point being there, if we're going through a huge crisis, feeding those people becomes a problem, right?
They eat stuff.
Right. You're not supposed to do that.
No.
So, and then that would reduce the number of people and keep the generator going. So, So that's the problem. I mean, that's the problem. Is how do you keep the generator going? Good. Oh, also one other thing. Okay. So, Dominic, just another thing. Hey, just because somebody asks a question doesn't mean we can all break this spontaneous conversation.
Come on, guys.
So I'm pretty sure all of you were talking about people turning a generator. So, the other thing being, how fast we turn the generator also determines how much electricity is produced. You ever been to the Science Center and they have that light that's hooked up to like those, and depending on how fast you turn the wheels, you get more lights and they turn on brighter and stuff like that. People can't turn the generator quite as fast as shooting a jet of steam at it can. So that's another reason there. Right? But regardless of how we turn it, it's got to turn, right? In a hydroelectric power plant like at Niagara Falls, what turns the generator? The water going over the falls, the water in the river, right? Or at Hoover Dam, same thing, right? The design is basically the same. It's just a matter of how you're going to turn the generator. Megan, go ahead. Say again? So, I have the answer. I'm just trying to frame how I'm going to frame it to you. Wait, do you remember when we did the calculations of average atomic mass, and we took into account like the percentage found in nature and stuff like that? If you look at the periodic table, question being, how abundant is uranium-235? If you look at the periodic table, the average atomic mass of uranium is 238.03, which means how much uranium-238 is out there? A lot, because why? Because the average is really close to 238. So we're talking about a very small percentage of the uranium that's out there is uranium-235. So the process that you go through to isolate uranium-235 from the rest of it, it's got to be, it's worth it from the standpoint of how much energy do you get out of splitting a uranium-235. But to answer your question, it's very rare. Less than 1% of the uranium out there is uranium-235. So we have to go through a pretty extensive process to isolate it from the rest of the uraniums, but the energy that we get out of it is worth it.
Is there any other material that's like similar to it, or is that?
The only other material that we know of that will do that is a plutonium isotope called plutonium-239.
So we are gonna run out of like atomic bombs.
Well, not necessarily, but technically nuclear power is not a renewable energy source. Because, Sam, eventually what's going to happen? We're going to run out of uranium-235, right? So, nuclear energy is not a renewable energy source. There's other issues associated with it, but it is not renewable, okay? Miriam, go ahead. So, for the atomic bomb, do you need a lot of uranium-235? Not one, right? Remember that we said that if you plug the mass of one atom in this equation, it's really not a lot of energy. Miriam, the biggest thing is, for the atomic bomb, you need to make sure that when these two neutrons come out of the fission reaction, what has to happen? They got to run into another uranium-235. You could, technically, I suppose. I don't know if we do that or not. I know that the two atomic bombs that we dropped, one was a uranium bomb and one was a plutonium bomb. They obviously work the same way. But the important thing for an atomic bomb being is that you have to make sure that when the neutrons come out of here, right? Oh, there it is. And when the neutrons come out of here, they run into the other uranium-235s. Okay? Now, for the power plant, that's not quite as essential. Okay? Because we don't need to generate as much energy to run the power plant. So when you have weapons-grade plutonium, right? Have you ever heard of that expression? Okay. There is weapons-grade plutonium. That was air quotes, in case you're watching at home. But the weapons-grade plutonium is much more closer to pure uranium-235 than the uranium that shows up in these fuel rods here. Okay? So more of those neutrons that are released run into more uranium-235s, more energy is released, blah, 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 blah. Chris, go ahead.
Right, two questions. First, was the plutonium one stronger than the uranium? Or?
I don't think so. I think they're both pretty similar. I know that, like, more people died in one than the other one, but I think that was more like the city. Yeah, like how many people were there and stuff like that.
Right, and then the other one was, is nuclear fission like best, like the most for like generators to work with, like?
Well, not necessarily. It doesn't necessarily work any better or worse than a coal does. It's just a matter of what do you get out of it. By burning coal to heat that water, you get a bunch of pollution or air pollution. By doing fission to heat the water, you get radioactive waste. It's like, what do you want to do? Okay. But it's much more reliable than like solar or wind or water or something along those lines. Okay. Andy, go ahead.
I have two questions.
Good.
Are those like uranium rods releasing heat, or is it just?
Well, are the uranium rods releasing heat? Yeah, they're releasing energy, which we use that energy to heat the water. So yes.
And do they change the water?
No, not really, because this water here, if we look at it, this water that's in the reactor, it never touches anything else. It's in an isolated sort of system.
So where does the waste come from?
It comes from here. Because when that fission occurs, you're left with this, right? You're left with these two. And these two aren't any good for fission. They're just what's left over. So eventually, these rods don't have much uranium-235 left in them, but they have the krypton and the barium, right? And that doesn't do us any good as far as fission is concerned. Okay.
How do they change the rods?
Carefully. So, and I wish I had a better answer for you than that, but that's biology. Carefully. And then when they're done, they pretty much put them in kind of what they consider to be leak-proof containers, and they pretty much store them on site. Okay? They don't really take it anywhere because nobody really wants to put it on a truck and drive it somewhere, in case something happens on the way. Great, good.
After someone drops a nuclear bomb,
Yeah.
explodes, and there's still an effect on the people hundreds, 100 miles away. Is that the uranium that affects?
No.
My mom told me that drop a nuclear bomb, people miles away still get affect cancer and stuff.
Right.
A couple years later.
Yeah.
That's not the uranium.
It's not the uraniums. It's not the uranium necessarily, because the uranium's not really there anymore. It's more the energy that got released. So the question was, the people that don't necessarily get killed by the bomb, are they still affected by it? And the answer is yeah. So Grace, for lack of a more scientific explanation, okay, what happens to people in a nuclear bomb attack is a really bad sunburn. It's just a matter of how bad is the sunburn. You get sunburned by radiation from the sun. Radiation is just energy that is given off. And remember, energy is the ability to cause change. The energy from the sun causes your skin cells to die, basically. That's what a sunburn is. They don't work right anymore. And that's why it hurts and stuff like that. Okay? If you got more energy, if you stay out in the sun longer, how bad of a sunburn do you get?
Really bad.
You get a really bad sunburn, right? If you are exposed to sun over a very long period of time, and a lot of it, the possibility of developing skin cancer shows up, right? Skin cancer is that the energy from the sun has gone into your skin cells, and the ones it didn't kill, it modified their DNA, basically. So now, when they go to produce another skin cell by mitosis, right? Does that sound familiar from like 7th grade or whatever? It doesn't make a skin cell anymore. It makes something different because its DNA is different because it was modified by the energy from the sun. Does that make sense? Yep. The sun causes sunburns and skin cancer over years worth of time because how far away are we from the sun? Say again? An astronomical unit, which is pretty far. It's like 93 million miles. But just think, even at 93 million miles, there's still enough energy getting to you to cause sunburn and possibly cause cancer. Now, a nuclear bomb is nowhere close to the amount of energy that the sun is giving off. But how close are those people to the nuclear bomb? A whole lot closer than we are to the sun, right? That's the idea. It's not any different than what happens to you when you get a sunburn. It's just a matter of how close are you and how much energy do you actually get, right? Now, instead of being 93 million miles away from the sun and getting skin cancer over a period of 20 years, right? If you're 100 miles away from a nuclear bomb blast, you get skin cancer in a year because so much damage has been done to your cells that it just messes your body up. Does that make sense? So it's not any different than getting a sunburn. It's just a matter of how close are you to it.
But if they're farther away, how does it get to the
Energy, remember we talked about last chapter, conduction, convection, radiation?
Yeah.
We said radiation, I could throw the node from one side of the room to the other side of the room even if nobody was there. That energy is just being released, and it's just traveling outward from the site of the bomb.
Dude, this may be like a stupid question, but is it like bright light?
Oh yeah, I mean it's light because that's a kind of energy. It's also heat because that's another kind of energy. But then there's also like X-rays and gamma rays, and it's just all this energy just, you know. So, okay, go ahead.
Krypton and barium are stable atoms.
Yeah.
Why can't we stay with
Because in those fuel rods, we don't necessarily use all of the uranium-235. We use most of it, but you get to a point where those neutrons are being released, but they're not running into enough uranium-235 atoms anymore. It's kind of like the battery's going dead. It's not like there's no juice left in the battery. It's just a matter of it's slowing my remote control car down so much that I'm just going to change the battery. Does that make sense? Okay. So yeah, there's still stuff there, but yes, those atoms are stable. Chris, go ahead.
In history, watched a video on like the atomic bomb, and it had like pictures where it was just people, but they were just like carbon. Is that what would happen?
Pretty much. I mean, that's what your body is made out of, basically. It's basically like the ashes of fire.
Yeah.
You know, it's
People are become like ashes.
pretty much you heat them up enough. That's what happens when you cremate people when they die. So,
Like
all right.
grandma.
Hey, two more and let's go. That's good.
Like in the atomic bomb, like they showed us like how like it works like inside. It had like two like hemispheres of like uranium with like this, and then like it was sort of they clash together.
Okay.
How does that work with the neutron?
Not really sure, because I don't really know the mechanism how the atomic bomb works, but somehow they have to start a fusion or a fission reaction.
They
Somehow.
start that by colliding.
I mean, could be. Never mind something. I mean, a fission reaction is something running into that nucleus. So, I don't know exactly how though.
I just thought it was a sport.
So, I don't know. I honestly don't.
No, it's something like that.
Miriam, go ahead.
That was just sport.
Hey. Easy. Miriam, go ahead. Perry. Yeah.
Is that like most of them that have been spilled all over? We just have to.
Probably. Oh, well, generally they don't build nuclear power plants close to big cities for that reason. But we'd have to, yeah, Cleveland, we'd probably be okay because we're pretty far away from that power plant. Like it takes to get to Perry is at least a good 45 minutes to an hour, right? Closer to Pennsylvania. Right. Well, I wouldn't say that, but our risks would be reduced, I would say. Lauren, one more. Good.
Okay, so you watched the video on the atomic bomb in history, right? And they said that they had to detonate it like before it hit the ground. Why?
You can do either way.
If
Because
it's-
the energy that gets released, it goes into the ground, but the temperature like reflects it.
Yeah.
Where if you like detonate at the ground, the earth would take most of the energy. They weren't trying to make a wipe out.
Yeah, the energy just goes in all directions, Lauren. So if you detonate it like real close to the ground, you're basically just going to make a big crater in the ground, you know. But if you detonate it above the ground, not all that energy gets like shot onto the people on the ground, and that's, you know, unfortunately that's what you're trying to do if you set off an atomic bomb, is kill people. So, you know.
The Amazing Race did up to the place where
Still pretty. So.
oh, we watched the video on Instagram. All the like kids, like there's like kids that like I like that stuff. So
It's actually, I read an article
they're
once.
scared.
I read an
don't
article
know
once.
why.
Does anybody was Hiroshima first?
Yeah.
Yeah.
So there was this guy. I read an article that there was a guy who was in Hiroshima, and he was there when the first bomb
Like an
went off.
American guy?
No, that's the Japanese guy. Because he was in Hiroshima when the bomb went off, and you know he got injured, didn't die, and he got injured, but he was from Nagasaki, so he got injured and he went home, and then 3 days later they dropped the bomb on. So he was there and he survived both of them. He just passed away like last year. So yeah.
You like knew him?
No, it
Oh,
it was in the paper. It was in like the newspaper.
Well, you made it sound
No,
like you like
he wasn't like my bud. He wasn't like my bro. No, it was in the paper. Like, you know, he like it said he died like last year. Yeah, but yeah, he was in Hiroshima when the first bomb went off, and he got kind of injured, so he went home. Obviously, I mean, there's no really use to stay there because there was really nothing there anymore. So he went back to Nagasaki, and he was there when they dropped the second bomb. I believe his family had severe casualties, but I don't know for sure. So look him up on the internet.
Did he die of cancer? Like, what is?
Yeah,
Well, like no one's expecting it in the Great Lakes region. And then,
I mean, we probably wouldn't get vaporized right away, but we'd definitely be in that high radiation zone.
I'm pretty sure that was like 4 miles.
All right. So, on the other side of things, while fission is taking something big and splitting it apart, there is another type of nuclear reaction that exists out there called fusion. And because you know because you know English, you probably could figure out that if we fuse something, what does that mean?
Take two things and put
You
them
take
together.
two small things and put them together. So two small nuclei are combined to form a nucleus with a greater atomic number. Very much like during fission, a small amount of mass is lost during this reaction. But because of the whole mass-energy equivalence idea, that mass gets converted into energy and it produces a very large amount of energy. However, there are some limitations on nuclear fusion. Okay? So, let's go to this picture. It's a pretty high-tech picture here. It's like very artistic. This might have been made like on an Apple IIe computer, which was older than you guys. So. But the gist of this picture being, we take two small nuclei. They're both hydrogen nuclei. What designates something as a hydrogen nucleus? What has
One
to
atom.
One
Proton.
proton. Now, these nuclei actually have some neutrons in them, so they're not the normal kind of hydrogen that we see out there most of the time. But these two hydrogen atoms come together, and there was this hydrogen nucleus that had one neutron, or sorry, one proton. This hydrogen nucleus that had one proton, and they come together and form another nucleus. How many protons will that nucleus have?
4.
How many protons will it have?
Two.
Two, because there was one here and one here. So that means that we took hydrogen and turned it into what?
Helium.
Helium. Because helium is a nucleus that has 2 protons. Okay? Now, once again, if you took a look at the mass of these two together, and then the mass of these together, you would find out that there's more mass at the beginning than there is over here at the end. And that mass gets converted into energy. But the trick here is this. Do these two nuclei want to stick together? No, because they both have what? They both have protons, means they both have what kind of a charge? Positive charge. Do these positive charged things want to stick together? No. Right? So, the only way we do this is if we make them stick together. Both of these small nuclei are positive charged. That means they repel each other. Okay?
Wait.
So, we'll fill it in just a second.
Okay.
Okay? So, the only way to get them to stay close is to do one of two things. Either you push on them really, really hard, or you make them go really, really fast. Okay? If you push on them harder than they're repelling each other, will they stick together? Yeah. Right? If you make them go really, really fast, can they avoid running into each other?
No.
No. How do we make really small things like this go really fast, Nick?
Temperature.
We make them get really hot. Okay? Sorry.
Yeah.
So, if you look at your outline, right? A says 2 small nuclei are combined to form a nucleus with a greater atomic number. Right? Then B says a small amount of what is converted into what?
Mass
It's
is
converted
converted
into energy. Okay? Small amount of mass is converted into energy. Very similar to the idea of what happens during fission. Okay? But fusion requires extremely high temperatures because all protons have a positive charge. So in order to get them to stick together, right, they must have a lot of energy. Right? This, yeah. Right? And then for number 3, this high amount of energy is only achieved at high temperatures. Can we do this on Earth?
Yeah.
Yeah. But the problem is the amount of energy that we have to put into these two to get them hot enough so they stick together is more than the amount of energy that is released. So is it worth it for us to do it? No. But if we could do it at a lower temperature, what would be some of the advantages to doing fusion over fission? Well, no radioactivity except for the fact that it gives off energy, right? Okay? Anthony, go ahead.
Hydrogen, there's a lot of hydrogen.
There's a lot of hydrogen. Earlier we discussed how difficult is it for us to get uranium-235. It's a pretty hard process to get uranium-235. But there's a lot of hydrogen out there. Okay? What else? What are we making? Helium. Is that a big problem? Not really. Okay, it makes your voice funny. I mean, if we made a ton of helium, yeah, that would be a problem. So it would start, like, taking the place of oxygen in the air and stuff like that. But
And everybody would have
big picture-wise, we would have to make a lot of helium for that to happen. Okay.
You have to get a lot of those, like.
True. And if we just had a lot of balloons, we'd be good. So.
Yeah, should that we're running out of helium?
Say again.
Like the Earth itself is running out of helium.
Okay.
Well, I guess I shouldn't say that. Hold on to that.
Maybe like fusion, like four things fuse it together to make
Yes,
oxygen.
that starts happening.
So
But, so Chris, that was a good question. Could we take like 4 heliums and fuse them together to make oxygen? The answer is yeah, we could. Except, how much energy do we have to put in to get 2 hydrogens to stick together? A lot. How much hydrogen do you have to put in to get 4 heliums to stick together?
A lot,
A lot more, right? Because now you're talking about 8 protons that are trying to repel each other instead of just 2. Caroline, go ahead.
Is there a difference in the amount of
Yes. Actually, at a per pound basis, if you want to look at it that way, fusion actually produces more energy than fission. So it's in our interest to try and come up with a way to do fusion without having to put so much energy into it, because it does give off more energy than fission does. But right now we haven't been able to do it at a reasonable temperature, basically. Okay?
how,
Good, good. Oh, sorry. Good,
how
good.
did somebody like figure it out if you can't do it?
I mean, when you look at what's in, actually, that kind of transitions us into the next. They kind of transitions us into the next section as well. So, yeah. Good.
then what stops us from just creating uranium 235?
Because now to get uranium 235, you have to stick 235 protons together, right? That's can't do that so much.
For the last one in the universe.
Oh, in the universe, that temperature is generally only reached where?
In the stars.
Well, not just the sun, but in stars. Okay?
That was a good lead.
And that not naturally, no. Like I said, we can't do it, Miriam, but the amount of energy that we have to put into it doesn't justify us doing it.
Oh wait,
So, that's a nice transition into the next part. Okay?
Very nice transition.
As I said earlier, I think may have said it yesterday, I'm assuming a lot of you guys have heard some of this stuff before, so I'm going to go through it kind of quickly. If something is too fast, if you don't get something, you don't quite understand something, stop me and we'll talk. Okay? But let's start off with the star. Okay? How does a star start off? Okay? A big collection of gas and dust. Okay? So scientists look at different types of stars, study the energy they give off and their composition. So Chris, we can look at a star, and based on the light that it's giving off, the energy that it's giving off, we can tell that there's helium there and there's hydrogen there. Mostly. There's some other things, but mostly it's hydrogen and helium. You start putting it together and put pen to paper and go, okay, well, this must be what's happening. And then we go to the laboratory and go, okay, if this is what we think is happening in a star, let's see if we can do it here. Right? So that's kind of how we get to that process. But we can look at these stars and basically tell what's there based on the kind of energy that they're giving off. And we come to the realization that most stars are hydrogen and helium. Okay? So, start working backwards. Stars basically start as a nebula. And I think most of you may have heard this term before, but a nebula is a large cloud of gas and dust, right? Basically a bunch of crap. So, we did the first slide, we didn't have anything to write down. Okay. Oh, sorry. Packet that I gave you yesterday. Flip to page 4 of your packet, please. I apologize for that. That packet is multiple outlines put together, and on page 4, there's an outline that starts off with life cycle of a star. So I forgot to tell you that. Kind of important. All right, so stars start off as a nebula. A nebula is a large cloud of gas and dust. So it's matter, it's just spread out matter. However, we learned that all matter, regardless of how big or small it is, will do what? Gravity. So these small specks of gas and dust start gravitationally attracting each other. Oh, there's gravity. There's gravity between every 2 objects in the universe. We don't think of it that way because Earth's gravity dominates us because it's so big and we're so close to it. But if I take this ball and this dry erase marker, right, and I move them out way, way, way far away from other stuff, what will they start doing to each other? They will start attracting each other, and they'll start moving closer to one
But in
another.
space,
Okay? If we can get rid of
space, not
not on Earth, because Earth,
yeah,
Earth's great, yeah.
Yeah,
If we can
not-
take them away from all other big things, okay? So that's what starts happening, is that these little specks of dust and gas start gravitationally attracting each other. Is it a big gravitational attraction? Not at first, no, because the masses aren't very big. But if there's nothing else to stop them, what are they just going to start doing, Sam? They're going to start attracting each other. Eventually, right? Eventually, especially if they attract each other over very, very long distances, even though it's not a strong attraction. If you're, even if it's a very small gravitational attraction, if these two specks of dust are attracting each other over like 1,000,000 miles, how fast are they going to be going by the time they run into each other? They're going to be going very fast because gravity causes acceleration, remember? And if they're going really, really fast when they run into each other, isn't that the recipe for fusion?
Yes.
Right? So what happens is these gravity things start pulling each other together, pulling each other together, pulling each other together. And as they get closer, they're getting faster. And as they get faster, they run into each other. And as they run into each other, fusion starts to happen. Now, what has to happen at that point is we have to strike a balance. There has to be a balance between the force that gravity is pulling them inward and the force that the energy of fusion is pushing them outward. If the inward pull of gravity and the outward push of fusion balance each other out, that's how we make a star. Okay? We refer to that little baby star as a protostar. Okay? And if the mass of the protostar is big enough, it will turn into a real star. Sometimes these things start happening, but it doesn't actually get to the point where the inward pull of gravity is balanced by the outward push of fusion, and we just end up with a big clump of stuff. Jupiter. Okay? Jupiter is a big collection of gas and dust, but it wasn't big enough to keep that fusion going to balance out pull of gravity. Okay? Anything else?
So, like, planets and asteroids are just star rejects?
Pretty much, yeah. They just weren't big enough to start to get that balance between fusion and the inward pull of gravity. All right, we'll pick it up from here tomorrow.